everyone. This is a research forum session. Oh, I hope people will come in instead of going out. Anyway, so let's get started. It's already 3 minutes late. We're going to have 3 speakers for this session, all about global routing system improvements. The very first one is by Mr. Valencius, if I did it right, on the wide area route control for distributed services. So Valencius is a graduate student at Georgia Tech, and we just talked, you're the 4th-year students now, right? Yeah. So let's just, without further ado, let's get started.
Hello. So this is a joint work with Nick Filmster, Akihiro Nakao, and Jennifer Exford. And I'm going to talk about wide area control, which is basically a fancy name for BGP. And basically the context, what we're trying to do here is that we see explosion of hosting in cloud and in hosting platforms. It's both in the conventional hosting and in the cloud setting. And the thing is that what we observe is different applications in cloud or in a hosted environment. They have different requirements for routing. Just the most obvious example is interactive service versus a bulk transfer service. One probably cares about cost, the other cares more about performance. And what we also see is that the cloud or the conventional hosting, they don't expose routing to applications. So basically, applications have no route control. So let me go into more detail of what's really happening. So on the left, you have here, cloud data center or any data center which hosts some applications, and you can see, interactive and bulk transfer applications, and you have a data center router. What happens is that internet passes on the routes to a data center router, and that data center router picks one best route, and every single application, when they try to reach some destination on the internet, they use the same upstream, more or less, as a rule. So what happens here is that these different applications use the same path, but it might be the same path, it might be too slow for interactive service, or it might be too costly for bulk transfer. So what we have to do is actually every single large data center, they have a lot of these upstream choices. And we pick only one, so it's an obvious deficiency of what the applications could have. And again, all packets from all applications to the same destination use the same path. Now, if an application really wants to have custom routing, if I have this interactive service that really cares about performance, or this bulk transfer that really cares about cost, I need to obtain physical connectivity to upstream ISPs. It means physical connectivity, it means contracts, and I need to establish routing sessions, and I need to obtain internet numbered resources from authorities to really participate in internet routing. For most applications, that might be expensive and time consuming. If I'm a startup, I don't want to really deal with all these things. So this is basically our solution in one slide. We propose a box, we call it Transit Portal. It's basically a fancy BGP router which connects to upstream ISPs and connects to clients. Clients connect to the Transit Portal in a transparent way. So for router A, you can see a green and red lines. These connections, they seem as direct connections to upstream ISPs with full BGP route control. So what happens here now is that when the internet announces routes to the data center router, this transit portal, it forwards them transparently to client routers, to virtual routers. And each of these client routers can make their own decision of which upstream they want to use to reach the client on the internet. So interactive service might use ISP1 for their path, and bulk transfer might choose, let's say, cheaper ISP, ISP2. So that's sort of in a nutshell what we have. It's sort of, sometimes I think of it as a BGP level NAT. So it's full route control for hosted cloud services. So that's sort of a motivation, what we're trying to do. And now I'm sort of going to go into more details. How do we connect to the transit portal and how do we scale it? How does our implementation looks like? And also I'll talk about the current deployment. We actually have it deployed in a couple of locations. And then I'll finish with future work and summary. So each hosted service must run its own router. That router could be either physical or virtual router. So in the setting like Amazon EC2, if you buy 100 machines, one of them could act as a router to get these BGP streams from the different upstreams and choose between them. Now, each of these virtual routers or physical routers connects to this transit portal. It could be, depending again on the setup, it could be a tunnel or a VLAN. If it's in the same data center, it could be probably a VLAN. And each such link to transit portal sort of emulates a dedicated connection to upstream ISP. So if the data center edge router has 5 upstreams, a application router could have 5 virtual links to transit portal, and each of these 5 different links would appear as if it's direct connectivity to upstream ISP. So routing sessions are also established from this virtual router to transit portal, and it's standard BGP interface to select the paths that the application wants to use and also announce the prefixes that it wants to announce. So this is how it would look like for a single application, single virtual router. So you have a transit portal, you have 2 upstream ISPs, ISP1, ISP2, and you have the virtual router that has these 2 connections. So from virtual router perspective, it seems as if direct connectivity to upstream ISPs, from upstream ISPs, they actually don't see the client. So you can imagine here many of these virtual routers in the lower part of the picture, and the upstream ISPs, they see just 1 link. So what we do, in our deployment, we just did simple test. Imagine initially we announce our prefix through ISP1. We have all the traffic going through ISP1. And then we see ISP1 is slow. We announce our prefix through ISP2, withdraw from ISP1. Our routing converges, and it happens as if the connectivity from virtual router is direct to upstream ISPs. And just to sort of show that it's the same as if direct BGP control. If you would do currently any experiments that you want, let's say to use one upstream versus the other, it would take in the internet about 15 to 60 seconds to converge. And this is what we see basically, that you have on the y-axis you have observation points, and initially you see around 75 observation points see a destination using upstream ISP1, and then when we change the announcements, it takes about 60 seconds to converge for the internet to route to a service through the new ISP. So it's comparable. It's no difference of current BGP. Just the main difference is the choice is pushed to the application. So now I'm going to get a little bit more technical and how do we implement it. So we want to scale this transit portal, and when I say we want to scale, I mean in our setup that we have right now, we want to support dozens of sessions to upstream ISPs and probably hundreds of sessions to hosted services. We also want to provide appearance of direct connectivity, or this transparency property, so that the applications again see this connectivity as direct connectivity to upstream ISPs. And the last point is we'd like to actually prevent clients from introducing excessive routing instability or leaking routes, etc. So how do we, when we have a box like this, how do we scale memory use? And for some of you, these tricks will look pretty standard, and we apply them. So we use Quagga routing suite to implement transit portal. We need to store and propagate all BGP routes from all ISPs. So we don't perform best path selection on our transit portal because we want this best path selection to be made by the client routers. And it's explosion of state if you store every single route. What we do to reduce memory consumption, we use a single routing process with shared data structures using some of the Quagga's features called route views. So just some numbers is, if we just use distinct BGP processes versus reusing the redundant information in BGP updates, we save about 30% in memory usage. It goes from 60 megabits per ISP of RAM to from 90 megabits from 90 megabits per ISP of RAM to about 60 megabits of RAM per ISP. We also need to scale CPU use. So imagine if the transit portal has 10 upstreams and we have 10 clients who want to connect to each of these upstreams, that means we have 100 sessions to downstream clients. Well, it's sort of the CPU load can get high. So we use standard tricks such as BGP peer groups, and actually we observe pretty nice numbers that it saves, from given 500 client sessions, we save from 18%, the CPU reduces to about 6%. So we can see that, for example, this was done with 2.6 gigahertz Xeon off-the-shelf server, and we can see that we can easily support 500 client sessions. One serious challenge is how to scale forwarding memory, because it's not only the RIP, but it's also FIB is exploding. So we connect clients with tunneling and VLANs, and these are from the perspective of transit portal. These are each link to a client is a distinct interface, and to curb memory use, we basically, instead of installing full routing table, these 300,000 plus routes to each forwarding table, we just install default, and it's enough for the simple routing, because again, transit portal doesn't make routing decision. The decision which ISP to route is made by virtual router, and by virtue of packet arriving on an interface that belongs to forwarding table for ISP1, it means that it needs to go to ISP1. So just to sort of show how does it look like, if we install full routing table, we need to use about 50 megs per ISP of RAM, and then if you just have default, you don't use any memory at all, almost. So the interesting thing that this platform is currently deployed, and we use just off-the-shelf servers, and we have 3 sites. We have one here in Atlanta, we have in Madison and Princeton, and we have numbered resources allocated to us with an AS number and a prefix. So if you look up this prefix or AS number, you might see us announcing either the full prefix or parts of it. And the original motivation why we started this project and why we got these numbered resources and why we're here in the research forum is because we actually do experiments of this platform. We give access to researchers. We give access to BGP control. So if you see something happening from these numbered resources and you don't like it, I guess you should come to me and complain. So the experiments that we have and we are going to have, we had IP Anycast experiments. It was very useful for them they were testing their applications to see how much it would benefit if it uses IP Anycast. They use it for performance measurements to announce the same prefix from multiple locations. We also use it in networking class, and I don't know how many of you will like it, but basically we give hands-on BGP route control for undergrads. So we don't allow everyone to announce prefixes, but they get full routing feeds, and they're very happy for them. It's a very exciting opportunity to see really how BGP works. One experiment that's still in the works, we're not doing this yet because it's a bit controversial, is BGP poisoning, and it's with the University of Washington. And they would like to actually, through multiple locations that Transit Portal is, to announce these poison AS paths so they can infer BGP topology through vantage points. So for example, if through route views they see a certain link between 2 ASs as observed, and they want to discover other links, they might want to poison the AS update introduced the AS, one of the AS in the past introduced as a one of the starting ASs. So the next update will avoid this AS set and maybe will uncover some other paths. That's still in the works because we're thinking how to approach Nano community to, how much should we ask permission and what will happen if we just do it. So that mainly would be used for topology inference. So in the future, we're working on more deployment sites. It's together with Genie project, which has many deployment sites. We're expanding together with Genie. We're trying to make TP more accessible for network researchers. So you might see more and more usage of this. And we're thinking of faster forwarding currently just off the shelf server. And another serious topic that's sort of research-wise what we might do in the future is instead of BGP interface, perhaps many applications would like more lightweight interface than BGP to select cost versus performance between paths. So in conclusion, there's limited routing control for hosted services today, or I could rephrase it that for researchers there is limited routing control since if you're a professor, if you want to do some BGP experimentation, and if he goes to guys like you, ISPs would say, sorry, who are you? Why should we give you BGP feed? So we provide this sort of low entry barrier for researchers to access BGP. And our solution is this transit portal, which is scalable enough for us, and its deployment is real. And you can find more information on the website that's on the slides. So if you have any questions, comments, or critiques, I'm happy to take it.
Yeah, you finished rather quick, so we got lots of time for comments.
Scott Librand, Limelight now. It sounds like most of what you're doing is giving a full BGP feed to the researchers, which is obviously a good thing for them to be able to understand stuff. It sounds like you have a fairly good understanding that actually announcing things into the table can be dangerous, and I'm sure you're aware of what happened in the RIPE region with some recent announcements there.
What
okay.
did happen? I don't know.
I'm not the best person to recount all the details. I wasn't involved, but there was some announcements made to test some things that caused a bug to be triggered in Cisco iOS and to knock down real BGP sessions in the real live internet. Mm-hmm. So there are real risks to announcing things into the internet, and I just wanted to get your take on what you guys are doing to address those risks and to make sure that the things that your researchers are doing are safe.
Yeah, that's a very good question. So I think the tools, the tricks that we are using are pretty much known to everyone. So we have, of course, we have filtering. We announce only our prefix. We have filtering to announce only from the ISs that we allow. So in this case, actually, there's technical detail. We connect clients with private ISs, and before we send anything out, we convert to our IS. And then when we want to do a more complicated experiment, such as poisoning, we will relax these routes as necessary. But still, given bugs, we can't know every bug in advance, and we can't filter these out. So that's an issue, but at the same time, I think it's a fair game. If some of our researchers will exploit some bug, then maybe it's better they exploit it than I don't know, someone else.
Any other questions? You have a question, or you want to come on? So maybe I'll ask a question. This is about the use of your peer group. We did some BGP trace analysis that actually showed peer group has both advantages and also challenges. So one detail your talk didn't mention is how many sessions did you put into each peer group to get the gain that you showed, I think, on the slide 17.
Yeah. So yeah, I guess Yeah, it wasn't there. It was, I think it was 20 different sessions, and we were scaling each session. So, for 100, when you see 100 clients, it means each client, there are five clients per peer group.
And the challenge. Oops. Okay, I couldn't figure out.
I think if you press the button, then it's disconnecting.
Oh, okay. Say that you have 5 peers in each group. If one somehow falling behind, then that's gonna hold up the whole group, not being able to move forward. That's what we have seen in real operational. I mean, from the BGP traces out of the real operational routers.
Mm-hmm.
So I was just wondering if you have run into this problem, and what's your solution to handle that?
Honestly, I haven't thought about it. I've heard of this problem. So what we actually do, so usually, for example, the minimum router advertisement interval is about like 30 seconds. So normally we wouldn't announce, but since we're trying to be as transparent as possible, we actually reduce it to just like 2 seconds in our setup. So we might get delayed by one of the clients. And I guess I don't know if we can do anything about it. I don't have a good answer to this question. I guess it's a real problem. But
hear me? Oh, yep. Forgive me if I ask a stupid question because it's the first time I heard about this project. So I try to understand the motivation behind it. I mean, the data center, you try to give the BGP table to the hosted application, or what exactly you try to achieve here?
So there are a couple of motivations here. So the example that I started with a data center is that, so if you look at Amazon today, for example, they have thousands of services running in there that are completely independent, managed by different administrators, and all these 1,000 services, they're using the same route to a destination. And what we're saying that probably perhaps there are applications who would not want to use the same route as every other application. One example could be a bulk transfer. So right now, for example, Amazon charges, I forgot, maybe 10 cents per megabit or per gigabit, per gigabyte of traffic. Now imagine there's a bulk transfer, some application that maybe is very price sensitive. That application might want to choose cheaper peers than the default set of upstreams. So this sort of application would this sort of examples, in this sort of example, the application would benefit from seeing what peers I can choose and maybe what cost it associates with each of them.
But then in this case, from the peer perspective, from the policy perspective, will the peer has to know all the routes?
No. So imagine, let's say Amazon is in Ashburn, in their exchange in Virginia, and let's say they peer with 200 guys. Maybe 50 of them. I don't know how many transit of them. They're theoretically, potentially transit peers. How many of them are settlement-free peers? But imagine you have 5. It's enough to have a couple. Let's say 5 transit providers, right? And one is selling 5 cents per gigabyte. The other may be selling 15, and this who is 15 maybe is faster. So the interactive service would probably pay more and pick this more expensive peer, while the bulk transfer will pick the cheaper one. Now, today Amazon picks only one for every single application.
But in this case, it sounds like to me that the application has to have some policy built inside, and then they have to understand the routes.
Exactly. That's the toughest part. That only perhaps the guys who really see benefit of it, they would need to have an instance of virtual router running, or physical router, depends on the load and stuff like that, and their operator will have to understand BGP. And that's probably the weakest point of this setup, is that this interface of BGP is not everyone wants to learn BGP. So not every application wants to learn that.
But I mean, sorry, then in this case, I mean, I'm not 100% sure what BGP buys you, right? Because all they can tell you is the next hop.
Well, it can tell you the upstreams. You know, if you so right now you have default in Amazon. Your server in Amazon has just the default. Now, if you would have 5 links and each of them would represent different upstream, you basically have 5 different next hops to choose from, and if you have cost associated with them, you can decide which one you want.
So then in this case, you're saying that you turn the application to a semi-routers.
Basically, we push routing decision from the edge of data center, from the guy like Amazon, to applications who want to take that decision. So we enable applications to take routing decision, or not applications, the application administrator to pick that routing decision, instead of Amazon deciding for every single application.
So then in this case, what BGP gives you is how many exit point you have, but nothing more than that. I mean, of course, you have some information you can get from BGP, but from the application point of view, all it knows is like, now I have 5 different exit point and to the next hop, and that's it, right?
you could go through the whole range, starting from just just having 5 upstreams. Then maybe you don't need BGP, 5 next hops, maybe then you don't need BGP at all. If you need, if you want some more sophisticated routing, you might need BGP, you might need full tables from all of them, and some routes you'll choose from one upstream and the others from other upstream.
Okay, thank you.
Any other questions? Okay, if not, let's thanks the speaker. And yeah, okay, come. To do this session, I never realized I have this challenge of pronouncing the speakers' names. I just couldn't get it right. So our next speaker is also from Georgia Tech. Georgia Tech really take advantage being local. Maybe how many the presentation requests you people send? Just these 2 or got in, or you get more?
I sent in 2.
You even send in to yourself. Gee. So the next speaker is I cannot make your first name. I have to say last name. Shrikant Sundaresan. Okay. So he's going to talk about traffic engineering, about autonomous traffic engineering with self-configured link weight. It's another student under Professor Nick Vermister. You can start.
Thank you. So good afternoon. So I'm going to talk about online traffic engineering using self-configuring link weights. This is joint work with Christian Lumazanu and Nick Feimster, Georgia Tech, and Pierre Francois from University Catholic Louvain. I don't know if I really need to motivate traffic engineering to this crowd, but so I'll be really brief. Intra-domain traffic engineering balances load across inside a network. It basically improves load balancing, which means that load is well balanced and you have low utilizations throughout the network. That improves latency, end-to-end latency inside the network, resilience to traffic surges and link failures, and also available capacity of the network. And a typical objective function, and one which we will concern ourselves mainly today, is to minimize the maximum utilization over all links inside the network. So a brief outline of the talk. I'm going to first talk about what we think a good traffic engineering, intra-domain traffic engineering protocol should do. Well, it should have a good traffic engineering protocol should have 4 fundamental properties. It should be responsive, which means that it has to have the ability to react to fluctuations inside the traffic demand fluctuations inside the network, and it should do so in a timely manner. It should be stable, it should react to fluctuations, yes, but it shouldn't do so in a manner that induces instability. It shouldn't move traffic around without taking into consideration stability issues. It should perform well over a wide variety of traffic demands, network conditions, link failures, etc. And most importantly for us, it should make absolutely no prior assumptions about the graph, the network topology, traffic patterns, or anything about the network state. So I'll briefly go through the two main classes of intra-domain traffic engineering protocols. The first one is offline traffic engineering, which, for which example, I'll use the IGP weight optimizer proposed by Fodes et al. About a decade ago. So the way the weight optimizer works is that you have a topology, you have the traffic demand that you expect in the topology, and then you feed that to an optimization function, which will give you a set of link weights which you feed to the network. And if the assumptions about the topology and the traffic demand holds, then they show that you do get very good load balancing. Well, so it is not responsive because you really can't change link weights according to changes in traffic demand. It is stable because you don't have to change link weights often. You do so only once in a while, so convergence and other issues don't come into the picture. Well, there is a question mark over performance because although they do show that when assumptions hold about the traffic demand, the topology, it performs well. We don't really know. Performance can get suboptimal when the actual conditions differ widely from the assumed conditions. And it is not configuration free because you have to configure link weights and you have to trust the link weights that you get from your optimization function. So the other class of proposals are online proposals, and one of them is MATE, MPLS Adaptive Traffic Engineering, proposed by El Walid et al., also about a decade ago. So the way it works is it sets up multiple MPLS paths between each source destination pair, and it adaptively routes traffic through them. It is responsive because it is able to handle changes in traffic demands online. Although we haven't been able to evaluate it ourselves, published results do show that it can do so in a reasonably stable manner, and it can handle changes in network state, traffic demands, but unfortunately it is not configuration free either, because if you think about it, you have to set up the MPLS paths in the first place. And once you actually have good paths set up, it seems to work really well, but it is not really understood how you can come up with those set of good paths. So why do we need a configuration-free traffic engineering? Well, for one, it gives us flexibility in that you need absolutely no knowledge about traffic patterns or even the network. You don't need to know anything. You just need to deploy the protocol. And it reduces the risk of poor configuration, which is very important. So we propose Sculpt, which we believe is a completely self-configuring and adaptive traffic engineering solution. The main selling points for Sculpt is that it requires absolutely no initial configuration. We start Sculpt with a set of random weights, and then it just configures itself according to the topology and the traffic that it sees. Experimental evaluation shows it is stable, responsive, and robust to failures. And the way Sculpt works, it works by dynamically adapting link weights online in response to traffic patterns. Okay, now I'll go a little bit deeper into Sculpt, this part of the talk. So, like I mentioned, Sculpt works by updating link weights online. The question, the most important question we have to answer here is, how can you actually do that using link weights and also in a controlled way? Using link weights for traffic engineering doesn't really have a good reputation going back decades. So the main reason is that it wasn't obvious as to how you can use link weights in order to get fine control over traffic diversion, how we can divert traffic in a fine manner. So the obvious way if you have a congested link and you want to divert traffic away from it, the obvious way to do it is to increase the link weight of the congested link. The question we answer is how much do we have to increase it by? So if you do too little, nothing happens, and you're back to where you were. If you do too much, you actually divert a lot of traffic away, and that can lead to instability. So a solution to this is to use the key metric of the congested link, and I'll illustrate that with an example. So if you look at this topology here, you have two source destination pairs, AB and CD. And the way the link weights are configured, both A sends traffic to B through the middle link as well as C. So if you assume that that the thick red link is the most congested link, Sculpt tries to find the key metric of the red link. So we define the key metric as the difference in cost between the alternate shortest path that avoids the congested link and the current shortest path with the congested link. So the shortest path for AB right now is the path that passes through the red link, and the cost of that path is 2 plus 1 plus 4, that is 7. Now the alternate path is denoted by the dotted line, and that has a cost of 10. So the key metric for the congested link with respect to the source destination pair AB is 10 minus 7, which is 3. Now CD also sends traffic through the congested link. So let's calculate the key metric for CD. The shortest path right now for CD is 3 plus 1 plus 2 is 6, and the alternate shortest path, again showed by the dotted line, is 11. So the key metric for CD is 11 minus 6, that is 5. Now Sculpt works by updating the congested link with the smallest key metric. I'll go into why. So if you assume that the chosen key metric is the smallest one, that is 3, this is how the traffic pattern will change in the network. Now AB has two shortest paths, both of which cost 10. So with ECMP, AB's traffic gets split, and a little bit of traffic is diverted away from the congested link. However, it's important to see that CD's traffic does not get split. The minimum link weight update that you need in order to divert CD's traffic is 5, and we only updated the link by 3. So if you consider the case where if you had chosen 5 as the metric to apply, this would have been the resultant traffic flow. Now the shortest path from A to B changes. It's now completely through entirely through the top link. And for CD, now we have an ECMP path that uses the original congested link and the link at the bottom. Now, if you look at it, we have actually transferred a lot of traffic away from the congested link. We have transferred all the traffic from AB and about half the traffic from CD away from the congested link. Now we believe that the way to get a stable solution is to divert the minimum amount of traffic away from the congested link. So that's why Sculpt uses the smallest key metric across all the source destination pairs. Okay, now we'll go into stability and responsiveness and how Sculpt is designed in order to give you those. So like I mentioned in the example, you choose the key metric value that is the smallest across all your source destination pairs in order to give a stable solution. So the congested link potentially has many ingress-egress pairs, source destination pairs that pass through it, and each path has potentially its own key metric value k. Of course, there could be non-unique values, but we won't go into that right now. Intuitively, applying any link weight update k to the congested link would deflect traffic away from the congested link for all the source destination pairs that have a key metric value of less than or equal to k. So in order to make sure that we move minimum traffic away, we choose the smallest key metric. So there could be another stability issue. What if traffic is diverted from a congested link onto another congested link, and that makes that the most congested link. And this is a ripe situation for oscillation. So the way we deal with that is we maintain a set of congested links that are ordered based on residual capacity, and we make sure that when we compute an alternate path, it does not take into consideration the links in that set. So Sculpt explicitly searches for low utilization paths with higher residual capacities. And this solution also accounts for skewed link capacity, so that you don't actually transfer traffic onto a link that has a very small capacity, which could potentially shoot its utilization way up. So we have another patch, if you can call it that, to improve stability, which is to use multiple topologies. So we assume that we can use multipath and that routers can maintain multiple routing tables, which is basically having multiple layer 3 topologies over a single physical topology. And if you assume that each of them are independent of each other, so each topology has its own set of link weights and its own set of paths. And incoming flows can be hashed uniformly to any topology. And so basically what you have here is your traffic demand has been divided across n topologies, if you set up n topologies. And Sculpt only updates a single topology at a time. So that reduces the amount of traffic that you divert in any one iteration of Sculpt. So responsiveness. So it's easy to see that if you keep update, if you run Sculpt periodically, if you allow link weight updates periodically, it keeps moving traffic away from the congested link. And it needs to know the congested link in that iteration, but once you know that, and there is an alternate path, Sculpt guarantees that you move some traffic away from the congested link. And so it is responsive. So we'll move on to the evaluation. So we evaluated Sculpt using simulations, and we wrote our own flow level simulator, and we evaluated it over multiple AS topologies that we derived from rocket fuel. And we tested it over a variety of traffic demands, network failure events, and traffic surges. And we compared it to various flavors of IGP weight optimizer. So the different flavors are you have a link weight optimization for a given topology and one set of traffic demands, multiple sets of traffic demands, and also multiple link failure events. And also to the basic Cisco default solution that's InCap. And the baseline that we use is the optimum solution that is computed using the LP or the linear programming formulation for the given topology and the traffic demand. So our results show that Sculpt comfortably outperforms offline traffic engineering solutions. And we see in the plot, the x-axis are the different, you have the different the ASs that we tested it over. And the y-axis, it's the deviation of the maximum utilization, the min-max utilization from the optimum solution. So the blue line is Sculpt, and we see that across a variety of ASs, Sculpt is able to maintain its min-max utilization to within 15% of optimum. And I should mention here that we tested this over a wide variety of traffic demands, which pushed the min-max, optimum min-max from anywhere between 20% to about 80%. Convergence is an issue because this keeps running online, and Sculpt doesn't really search for an optimum link weight. It is a greedy search for a suitable link weight. So how long does Sculpt take in order to converge to a good state? We see that across all the ASs we tested, even if the starting condition was bad, in our case the starting condition was just the InCap weights, Sculpt converges to within 15 to 20% of optimum in about 25 to 30 iterations. I'll talk about the duration of iterations later. So it's important to know that even with a bad initial setting, Sculpt is able to converge within about 30 iterations. So we also tested Sculpt over a variety of stress conditions. One of them were using traffic surges, where we started off with a stable traffic demand, and then we randomly pushed up the demand between a source destination pair, multiple source destination pairs by a factor of 50%, and then brought it down to about 20%. And so we're trying to simulate random spikes and troughs in demand. And we see that Sculpt adapts very well to the changes in traffic demand. It's just not really a surprise, because it doesn't really care about previous state. All it cares about is current state, current link weights, and it tries to find a greedy solution that will improve the current state. Other proposals, like the weight optimizer that is optimized for multiple traffic demands, performs quite well, but it's rather suboptimal because it has to consider a wide variety of operating conditions. And since it's also hard to predict the nature of surges, I don't know if that solution is even feasible. And we tested it similarly for link failures with up to 3 link failures, and Sculpt again performs really well under these multiple link failure conditions. And the weight optimizer, which has been optimized for those specific link failures, performs poorly when there are no failures, which hopefully is the default case. So I did talk about the protocol being configuration free. So there are a few parameters that Sculpt uses. One of them is how frequently do you apply the link weights. So that's the duration of the iterations. On the y-axis here, you have the deviation from the optimum, and on the x-axis we have the different frequencies of link weight updates that we tested. So we see that it's fairly stable across different ASs. You change the frequency of updates from about 2 seconds to about 2 minutes, and Sculpt performs. I mean, the performance line is fairly flat. It stays within 15% of optimum. Other parameters that we tested it for the number of topologies to divide the traffic demand, and as long as it's greater than 1, Sculpt performs well. So quick recap on how Sculpt compares to the state of the art. It is responsive because it's online, and although it searches for greedy solutions, it does so in a stable manner. It performs well over a wide variety of operating conditions, and more importantly, it's actually configuration free. So I'll talk about some of the implementation issues that Sculpt can face in a real deployment. So we think that Sculpt can be implemented in a distributed manner or in a centralized manner. In the distributed manner, routers already support multipath, and you need you can have bits in the IP header in order to choose a topology. You also need frequent SNMP-like updates. However frequent you want to apply your link weights, you need link utilization updates. In a centralized implementation, we could do it with OpenFlow switches and NOx controllers that computes the key metrics and also pushes the link weights or the paths to the routers. And we were actually fairly successful in implementing this over a very small experimental 4-node network. Some of the challenges Sculpt would face under a deployment scenario would be the main thing, in my opinion, is IGP convergence. So if you're going to do link weight updates over a few seconds, every few seconds, then IGP convergence becomes a real issue, especially in large networks. However, Sculpt seems to perform well even when you only update link weight updates every about 100 seconds. Also, Sculpt can be configured to be threshold triggered, in that you don't want to run these link weight updates unless you see the maximum utilization in your network going above a certain value. Flow rerouting, packet reordering is an issue because if you update paths frequently, packets could get reordered, and that's not a good thing. And one solution to this could be that you pin existing flows to routes so that there is minimal packet reordering. Router overhead is pretty high because it needs to support multiple routing tables and also frequent link weight updates. And if it's a distributed implementation, it needs to be able to actually compute the link weight updates, the key metric, which is actually not it's actually quite an intensive computation. So that's one area that we are actively working on right now is how we can do a fast computation of the key metric. So we believe that Sculpt would be a good fit in a scenario like data centers where you have short-lived bursts as well as long-term MapReduce style traffic surges, because Sculpt can handle these kind of traffic surges very well, and it doesn't need any prior information. And also in networks where frequent updates is an issue, you can have a threshold triggered updates, which I mentioned in the last slide. So in conclusion, most of the current TE proposals required specialized configuration, which we believe is bad because it's easy to go wrong. We believe that Sculpt is the first stable traffic engineering proposal that is essentially configuration free. And the way it works is by modifying link weights online in an intelligent manner. So we showed that it actually delivers excellent performance over a wide variety of ASs, traffic scenarios, and network states. So if you have any questions, you can contact me at this email ID, and I'll be happy to take any questions right now.
Any questions? I have a worse, maybe a trivial question. When you did the evaluation using different ISP or AS configurations, I saw that the different curves look differently, some much lower, some much higher. I was just wondering if you could elaborate what are the major differences in their topology that led to different, not this one, yeah, the later, the curves, yeah.
This one?
No, that one, the next one, next. Yeah, like this one, for example.
Oh, this actually shows that it doesn't matter too much at what frequency do you update the link weights.
But
So-
why different topology end up with different, like,
so
heights?
okay, so
Like what's
so
special with the Abilene?
Yes.
Is the last one? What's special with the
So,
6395? Is it-
okay, for Sculpt to work well, it needs choice. It needs a lot of source destination pairs. It needs a reasonably sized network. So if you think about it, if you have multiple, we say we achieve granularity in shifting traffic away from the congested link. The only way you can achieve granularity if you don't have flow level control is by having multiple source destination pairs.
Right.
And if you don't have it, then you're going to shift larger bits of traffic away from the congested
Vice
link,
versa.
right? And that could cause momentary oscillation. And we believe that it's a difference in these topologies where you have, in certain topologies where you have good choice, when you have good alternate paths, it actually performs really well. But in certain other topologies, it may not perform really that well, depending on how much choice you have in alternate paths.
I see. It's good. Yeah.
It's Yuli from Comcast. I got a question, try to understand it. So I assume that this is similar to all other traffic engineering algorithms. So you will have to calculate from the source, right? The information for the matrix.
You don't really need any information about the matrix. All you need is updates about the link utilizations.
But then how do I know when I try to calculate it? Because I have to go to the destination. So then I should have the full table to understand.
You need the routing table, yes.
Not the routing table. What I'm saying is that in each of the entry or each of the prefix, I should have a cost associated to it, right? Otherwise, I don't know.
So you assume that you know for a given flow, you know what your destination is, and then you compute the paths using the shortest path.
Maybe if you get back to the Jeff Tremblay Videotron, if you get back to one of the first slides when you actually show your algorithm. Yeah, that one.
Which one? Okay.
So the issue here is, if you click again just to get the whole slide,
This one?
the issue here is A knows about 10 and 7, but how does get A, how does A get 3? Sorry, not 3, 5. A has to know about the shortest path from the point of view of C as well, right?
We assume that each router, or I mean if it's a distributed implementation, that it knows all the link weights, right? And it also gets information about the link utilizations. So it's able to get the most congested link and then compute paths. Like I said, it's the computation of the key metric is fairly computationally
Yeah,
intensive.
because that's a square N problem, because you've got to work to compute the SPF3 for all the routers
Yes,
at the same
yes.
time. So this is extremely intensive.
Yes, so we believe that a centralized implementation would probably make more sense in this case.
Yeah, another question I have in this case, like, I assume that like you will have some link state information passed by. I mean, the traffic information probably have to have some routing protocol to bring the information to the A. So every time you change the weight, then the router has to recompute pretty much all the weights.
So the thing about using the minimum key metric is that it affects a minimum number of paths. So we don't think that you need to compute all the paths. You just need to compute a very small subset of paths. So the advantage here is that you update only one link. You update only one link weight, and we choose that update so that you affect a minimum number of paths through that link. So you could potentially do it in a step-by-step manner. You don't really have to do all your computations again.
But then the question I have is, how does, for example, like in your diagram, how does router, I mean, who is actually updating from 1 to 4, for example?
So in a centralized implementation, you would have all of them reporting their link utilizations to the controller, and then the controller would compute the key metric, right, and would push the link weights to the routers.
Okay, so I got you. So you actually have another box, which is a controller, which will have to talk to all the routers.
In the current implementation, yes, we do assume that a centralized controller exists because key metric computation is fairly, it's not easy. Because we need to know all the paths that pass through a link, and that actually scales into the n cube.
Okay, thanks.
Okay, I guess, yeah, okay. Go ahead.
Ali from Rogers. I guess there are two input in the centralized solution. There are two input information. One is that he needs to know where the traffic is coming from, where is it going, in this case from A to B and from C to D. And he needs to know the congestion level on that link, right?
So it needs to know that there is a path, A has the shortest path through the congested link that goes to B, and C has the shortest path that goes through the congested link through D, yes.
That's right, but he looks at that from the information he's getting from the packets, from the traffic, right?
Well, you can get that from the routing table with your link weights, with your current set of link weights.
Right, okay, thanks.
Scott Librand. So am I correct in understanding that this is an iterative process that takes absolutely no information from the endpoints as to where their traffic is going, but just says, this link is overutilized, what's the next higher cost that I need to put on this link in order to reduce traffic, apply that, see what happens, if necessary, do it again? Okay, that's something that I think a lot of us do manually. I think an automated tool to do that is a good idea, and I like this presentation. Thank you.
Thank you.
Okay, let's thank the speaker, and okay. We have another presentation, and this time it's no longer George Tech, but rather from the French Telecom Orange, right? He's going to talk about how to speed up BGP routing table transfer.
Hi. Thank you, Alicia. This is joint work with Michael Meul and Renata Teixeira from France Telecom R&D and UPMC Sorbonne University. So I'm going to talk about a phenomenon which is widely suspected to be true with no hard evidence to back it up, something that remained uncovered for years, and I think it needs finally more attention. I'm talking about BGP routing table transfers. So people often say that BGP routing table transfers are slow, and So is this a myth or is it real? So in this work we show that, that it is true, and we explain why. So first, why do we study table transfers? Because slow table transfers can delay BGP convergence. So if I simplify, then BGP convergence involves mainly 3 steps. First, there is a change that is detected, then this change is propagated, and then it might result into a routing table update. So the propagation time can be very significant if an event touches many prefixes at the same time. This is exactly what we call a table transfer in this work, that is the change of a large number of routes simultaneously. So this can be the case of BGP session resets or failures, or even intra-domain events that cause too many prefixes or too many BGP routes to change at the same time. So are table transfers slow, and why? So first, the analysis of table transfers in a VPN provider shows that yes, they are slow, and they are even slower than they should be. And we even found that they are slow because of what we call gaps. There are periods of time in which no routes are exchanged between the routers. Then second, our controlled experiments with different routers from different models, exactly 3, show that these gaps happen in all routers. And we also, our analysis of a software BGP speaker shows that these, and also the discussions with 2 of the router vendors show that these gaps are due to what we call a timer-driven implementation. And finally, there is a third question that we ask in this work: can we make this table transfer fast? And the answer is yes, and we explore the limits, and we found that there are limits that are induced by the sending router, and also limits that are induced by the receiving router. So before I start, what are we measuring exactly? Here I just show two routers, sender and receiver. If for some reason, for instance, receiver loses its routes, then it needs to receive an entire routing table from sender, and the time needed for sender to send the routing table from BGP address route till BGP address bin is the table transfer we are measuring in this work. And of course, we also see the impact of the import to the RIB, and as well as the impact of the installing of routes on this table transfer time. So let me start with the analysis of the table transfers in the VPN provider that we study. So in this figure I show 7 table transfers that we trigger in a large VPN provider backbone. And I show the table transfer in the y-axis, and the black boxes show the transfer time, for 680,000 routes, something around 30 megabytes of data, and compare them to the baseline values that are what should TCP achieve, for instance, to transmit the same amount of data. As you can see, the table transfers are much slower than what should TCP achieve in theory. So in order to investigate this phenomenon, we just tap the connection between the 2 routers during the transfer. And what we find is that there are what we call gaps, that are periods of time in which no routes are exchanged between the 2 routers. These periods of time tend to be regular in duration and in frequency, and they account for most of the transfer time, something like from 90 to 99% of the total transfer time. And the causes of these gaps are not documented anywhere, so since we didn't have any control on the operational router, so we set up controlled experiments to investigate more on this issue. So here just our test bed, very simple. We have routes, we have each time 2 routers, sender and receiver. All in all, we test 6 senders and 2 receivers belonging to routers from 3 different vendors. And I'm sorry, in this talk I'm not going to name the vendors. So just I'm going just to name them vendor 1, vendor 2, and vendor 3. So each time we reset the session between sender and receiver, and we tap, of course, the connection between them to see the table transfer. And as well, we monitor the router's CPU load to understand what is going on during these gaps. So first, the first thing that we noticed is that these gaps arise in all the tested routers. These are the gaps I'm talking about. Here in this figure, I show the BGP messages exchanged as a function of time, and I just make a zoom on 10 seconds of route and table transfer. So the gaps are just these periods of time in which there are no routes that are exchanged. It's funny here because all the routers from the different vendors have the same behavior. And the funny thing as well is that the routers are always idle, almost idle, let's say, during these gaps. So since we didn't have the source code of these routers implementation, so we investigate on the software BGP speaker called SBGP because we had the source code. So our analysis showed that there is a timer that rate limits the sending of routes. And these timers expire each second, and this causes the table transfer delay. Then later discussions with the two router vendors confirmed our analysis on this, but then we had two different feedbacks. Vendor one said that it was unintentional, and vendor 2 said that it was intentional and it was a way to rate limit the table transfers to control the router's load. So what can we do to reduce the table transfer time? Here I put all the possible ways. Either we increase the sending rate or we reduce the table size. There are other, in the other proposals to reduce the table size. Here I focus on the first one. On the first factor, that is increasing the sending rate, and one of the ways is to remove this timer and just send the routes after the TCP ACK. If we do this, then the transfer time should be exactly as the baseline values that we talked about in the beginning. And actually we changed SBGP to make it like more event driven, to send the routes right after the TCP ACK. And actually 9 months after we started this work and after we reported the thing to vendor one released its new software and told us that it was more event driven, and we're going to test it to show how it behaves next. So vendors one, let me just say a word about the timer-driven implementation of vendor one. This was the feedback that we got from vendor one. They said that they have one process that formats the BGP routes and then puts them in a queue, and there is another process that drains this queue to send routes to TCP. They said that if for some reason this queue is full, then this process will go into like 2-second sleeping mode, and if you iterate on this procedure, then it will cause the gaps that we observed. So that's what we did, is that we tried to go towards an event-driven implementation. So we have this event-driven SBGP, and as well vendors one fix that makes this sleeping process wake up after the TCP ACK. And that's what we're going to test next, to compare the vendor one implementation, the new and the old. So here I plot the same thing, the BGP messages as a function of time, and I take a zoom on 10 seconds. And this is the new implementation of vendor one. As you can see, there are still, it is faster, of course. There are still gaps. As you can see, the gaps look like we replaced the 2-second gaps with 1-second gaps. Maybe there's something I forgot to say, just to give an order of magnitude of the transfer time. So the transfer time for 680,000 routes, we used VPN routes, was something like from 1 minute 30 to 12 minutes, depending on the implementations. And 12 minutes is really a lot. And here I'm talking only about one single session, one sender and one receiver. So we try to investigate. This is something I already said. What I did is just that I plot the CDF of all the gaps during the transfer that are larger than 100 milliseconds. And there are two types of gaps. These gaps that last around 200 milliseconds. And there are also these gaps. So the old software had 2-second gaps, and the new one has still has a 1-second gap. So if we compare the new software with the event-driven SPGP, then the event-driven is of course much faster, and with this fast SPGP thing, it takes us 5 seconds to transfer 700,000 routes, while the fastest router takes 1 minute. And actually, I had feedback on Quagga and Quagga as well, because I didn't have the opportunity to test it. And Quagga is as well like event-driven. It doesn't have these gaps and sends the routes pretty fast. So here I end the first part of the talk. I put all the router, all the implementations that we tested. Again, the number, the BGP messages sent as a function of time. So I don't know. I'm really wondering why. Why we didn't hear about this behavior. But I have two explanations. But I'm not sure. First, I think that these codes were written like maybe, I don't know, 15 years ago, and then the bandwidth and the CPU were not the same as nowadays. And second, I think that all the BGP studies collect data, use data that are collected from different vantage points, and such kind of events remain local and do not propagate. Now I'm going to investigate on the limits. Now I just consider fastest BGP in front of real routers and see what are the limits. The first limit is the number of sessions. Here I test one router or one machine sending routes to n machines. So what I do is that I vary the number of sessions, and what we see is that there is little benefit here in an event-driven implementation when the number of sessions is large. And this is normal because then the limit that we hit is the CPU and the bandwidth. Then the second limit is the number of imported routes. Here we do experiments in which we fix each time the number of routes that are sent, and we vary the number of routes that are imported. We can do that are, we vary the number of routes that are imported. As you can see, if we vary the number of routes that are imported in the RIB without installing the routes in the FIB, then it delays the table transfer. The last limit is the number of routes that are installed, and this is a very, this is a very important limit. If we fix the number of routes sent and vary the number of routes that are installed, then as you can see, the transfer time can go from 10 seconds to 120 seconds, and this limit is induced by the receiver because then the receiver is so busy installing the routes that it delays the TCP ACK, and then we have a TCP limit. So as a conclusion, in this work we show that table transfers are slow because of gaps that are caused by a timer-driven implementation. We show that faster table transfers are possible with an event-driven implementation, but there are limits that are the case of routers with multiple BGP sessions that are updated at the same time. Also, the important, if routers, the receiver imports or installs routes, then this might be also a limit. And I think that there is here a compromise to make between router loads and fast stable transfers, and that maybe the best configuration depends on the network, and that this behavior that is not documented and this hard-coded solution is maybe too limiting. So if you want to get more information, and thank you, and if you have questions.
Do you take questions now, then?
Yeah.
Okay, let me go through the questions one by one. First of all, one thing you didn't give details on in the presentation is the type of TCP you were using and the options. Does your detailed paper give that set of information? Because traditionally in the benchmarking work that we've done, see the benchmarking working group, which does this on a single node, TCP actually makes a difference. If you look at papers, as I'm sure Alicia knows over the time period, the TCP makes a significant difference. I didn't see that in the presentation. I assumed.
Okay. Here the problem is not a TCP problem. It's really a BGP process problem. The sender sends the routes, the TCP does its job, the receiver sends the TCP ACK, and then the sender doesn't do nothing.
Your assurance did not answer the question.
Sorry?
Your assurance did not answer the question. If perhaps I did not carefully state the question. The question was what parameters you set on your TCP, and if that information was in your paper that you had it, since it wasn't in your presentation.
No, I did not put the TCP parameters, but I can get them for you if you want.
That would be useful information to compare it against other work that has been done. For 5-10 years ago, Cisco improved its by changing its TCP parameters. Other people have improved their work by changing their TCP parameters. Knowing what parameters you start with will give me a baseline to evaluate your work. Just that's the history of the stuff that has been done within the last 10 years.
Yes, but I think there is something I'm not getting here. I said that the problem I'm talking about here is not about TCP. You can test any TCP parameters you want. I mean, it's about transferring 30 megabytes of data. If you take FTP, it would take 3-4 seconds. Here, I mean, I don't see why TCP is an issue. The problem here I'm talking about is about an implementation. It's about an implementation behavior that we saw on routers from 3 different vendors. One of the vendors even changed its software, and I'm sorry, but there's something I...
Okay. Second question, when you say an interrupt changes that you made, did you change the timing of the software to immediately send the ACK after you had it? How did you change that? The details were lacking in your presentation, and those are, as you said, useful details to understand. If you could elucidate that carefully, it would help again in comparing your work with other work that has been done.
Okay, I just removed the timer, and the BGP router. Actually, with this simple BGP speaker, there was a limit of the number of packets. For instance, the timer will fire each time I send 500 packets. Right, so it's the simple BGP speaker is different from what router vendors told us. So it's a different issue, but it looks the same. There is after each 500 packets, there is this fire with this timer which fires and which starts, and then I wait for 1 second, and then I send 500 packets, and then I wait, and then I send.
Did you discuss with the vendors why they had the 500 pause? in their packets?
What? Sorry?
Did you obtain the reason why the vendors put in the 500 pause? Because obviously it was a
Actually,
put in.
the 500 is not with one of the vendors. It's with the simple BGP. It's an open source software BGP speaker. For the vendors, they said that what they did is they make the BGP process send the routes right after the TCP AG, and we tested it, and we still can see gaps. My guess is that it went event-driven, but there are still other events that cause other timers. I think that this 2-second timer that was before was hiding another timer-driven behavior, which lasted 1 second. So what they did, the feedback that we had from vendor 1, 9 months after we opened the case, was that, oh yes, it's true, there is a timer-driven behavior, and it's exactly as we guessed. So they confirmed our analysis, and when we tested, we found that there are still timer-driven behavior. There is still a timer-driven behavior in their implementation. But we did not recontact them again to talk about this issue.
Okay, so normally what people have reported, by the way, my name is Sue Harris, and I'm the IDR chair, co-chair. So most people, when they talk about this, some of this load sharing that you're seeing is actually pre-planned. And what I'm trying to dig out, you'll also find one of the few benchmarking specs on this, or the definitions come from me as well. So what people have told me in this time period, and I'm always interested in seeing new statistics, hence my questions of interest, is that they do this for a reason. BGP is when you process as Van Jacobson said, there's always self-synchronicity in the network that is worrisome. And it is the self-synchronicity that they're trying to protect against. So this throttling of BGP is based on that particular issue.
Yeah, that's what I say in the conclusion. I mean, okay, there must be a reason, but maybe it would be a good idea if we know about it. And besides, I think that since the router's CPU, since the capacities are getting much higher now, maybe we can change something. And transferring 600,000 routes in 12 minutes, maybe we can do better with nowadays capacities. That's the only idea we...
So is the reason why you're pushing toward that better BGP convergence, and have you actually tested that the transfer relates to better BGP convergence? Most people have found that the transfer is not necessarily the same as BGP convergence.
Yeah. In this point, I 100% agree. But I think that there are some events in which the transport can be a problem. I read papers, stat report, for instance, that if you have a shift of a large number of prefixes at the same time, then it takes really a lot of time to change. And also sometimes, I mean, it happens. The transport is part of the game. If I am a router and I lose my routes, then it would be better if I receive them faster.
Okay, so the object of your paper was simply on the transfer of data and not on its link to convergence. You did no convergence testing in this.
The main point is about the transfer, yes.
Yeah, okay.
And I say that the transfer can be part of the convergence, because people always assume that the transfer is like it happens instantaneously. So
people who do benchmarking usually don't make that assumption, and you're in that good genre and you've done good thinking work. I just wanted to hear the scope of your work, and it sounds like you've done a good study of a particular piece. And I thank you for your time.
Thank you.
Any other questions? If not, I hate to hold you up, but let me ask one question. I remember at the very beginning you mentioned, you say you contacted two vendors. One of them said they did this timer-driven because of consideration for the CPU load.
Yeah.
Now, do you have any sense about once one changes to the inventor-driven, these updates, I mean the table transfer, how much does that actually impact or doesn't impact the CPU load of the router?
Okay, I have this. I have it, but not here with me. But you see an increase in the CPU, of course, but you're still not using the whole CPU. It's like I won't say it's like 10-20% CPU used during the whole table transfer. I have the plots with the new vendor implementation and the old one and the CPU use.
I see. Okay. Okay, I guess this is the end of the session. Let's thanks the speaker. So I think it's beer and gear time. Thanks for attending.